He has an internship for
Good afternoon, everybody. Okay, great. In the lecture today, I'm going to go through at a high level the various steps involved in setting up a simulation and some of the concerns and choices that we have to make. So I'll leave it until next week before I get into some of the more technical details of things like specific types of error and how to measure them. But at least for today, it's just at a high level to talk about the main choices involved and give you a feeling for the reason why it's complicated to do these sorts of simulations. And just an update in the lab tomorrow. I think the computer rooms up there, which are almost finished being renovated. I think they've been finished, but they haven't been signed off by the building manager. So I don't know if we can use those rooms tomorrow. So just look out for announcements on Brightspace. I'll send an announcement if we have to switch to a different room or if we have to make some other plans. If people have problems installing Abacus, you can ask me questions after this lecture if you want, or you can ask questions on the discussion forum, or you can email me. Any questions? Great. So what is the first step in creating a simulation? So real life is really messy. So whatever we've talked about before in the first lecture, heart valves or wind turbines, they're just really complicated. There's lots going on. There's lots of physical phenomena or chemical phenomena or all sorts of interesting and strange coupled physics. And so you just need to acknowledge that from the start, that real life problems are messy and complex and there's lots of answers. So for example, if you're interested in the thermal stresses generated in a brake disc. So the first step before we open up a software like Abacus or ANSYS or OpenFOAM is to define what's known as a mathematical model. So this is unrelated to a computer. So this is just a step we take before that. So this is looking at real life, which is messy, and making an idealization of that. And that idealization is called a mathematical model. To put it another way, we look at some real life problem and we figure out, can we approximately describe that, or at least some key phenomenon that we're interested in with maths equations. So can we define those maths equations? If we can define those maths equations, then we can decide, can we solve those maths equations to get something useful? And maybe there's certain methods suitable for certain problems, maybe it's an easy problem. So for example, if I have a steel rod and I apply force to one end and it's fixed at the other end, and I just want to check the deflection doesn't go over a certain amount, some critical threshold, then I would say, oh, well, actually, I know that beam theory gives the deflection is a function of the force. That would be my simplified mathematical model. I'll get some maths equations, and those maths equations I can just by hand determine the deflection. I don't need a software like Abacus, okay? So, but some types of problems that we're going to learn about are difficult to solve. And that's where we'll need softwares, numerical softwares. So going from the real life physical problem to the mathematical model introduces errors and assumptions. So for example, here, if this is the CAD of the brake discs and calipers, that might be some idealized geometry with perfect holes and circles. In reality, it'll have surface roughness, there will be manufacturing tolerances, the material may not be perfectly uniform, and there's many things that we have simplified out just by doing this step. It might still be a complex model, but we've simplified a lot out. So that step going from real life to this idealization, that's creating the mathematical model. That introduces errors, and those errors are called mathematical modeling errors or modeling errors. They're very distinct from another type of error, which we're going to talk about, which is numerical errors. So once we have the maths equation, when we go to solve those maths equations, if we're using a numerical method, like finite element method or finite volume method, they are approximate methods. They introduce errors also. So we have an idealization, that's approximation of reality. Then if we go to solve that using one of these numerical softwares, that introduces additional errors called numerical errors. And they're fundamentally two different types of errors. And both of them can make your model useless. So one key output of this our outcome of this module is understanding the difference between those and understanding how you can quantify some of them or assess the effect or impact. So these are mathematical modeling errors, and these are numerical errors. We'll come in a second. So the modeling errors are to do with you go from a real life problem to make the maths equations. It's any assumptions you're making or physics you're leaving out maybe. Whereas once you have that maths equation, just trying to get the actual answer to those maths equations can also introduce errors. Okay, so let's start off. I'll have one whole EV session. So just to get a sense of, do people have a feeling for the difference between these? So I will turn this on. So give me 1 second. Yeah, you go to polev.com and then the course code MEEN40150, or you can scan this with your computer. I don't think it's turned on yet, but I'll just, if people, see people putting their cameras down, then I'll skip over and turn it on. So just a couple of minutes just to have some interaction. As you see, I'll normally just do one of these sort of interaction sessions just to mix it up and make it a bit more interactive. Okay. 1 second, I have to plug this out. Okay. Okay, it should be active now, I think. Is it active? You're going to the just okay, go. Let me just plug this in. Oh, I might have clicked off again when I exited. Right. Sorry, the combination of Zoom and sharing my screen, they don't like to do. Yeah, I'll just give you a couple of minutes. So the question, if I can get this thing out of the array. Show height. Yeah, so imagine that you have to simulate airflow over a new design aircraft wings or takeoff, and you have to, the goal is to predict the lift and drag because you want to make sure the wing works. Can you think of mathematical modeling errors versus numerical errors, or what do you know? Maybe you don't know about those things, that's okay, but just to get your feelings on these. I'll just give you a minute. So this is people posting things. Another 30 seconds for people to finish off. You posted something that maybe you might think about, well, if there were mathematical modeling errors, can you think of what numerical errors might be? Okay, very good. You've got lots of answers now. So you can finish off posting if you're writing something. I'll when I get to the top again, I'll add them. And so I'll go through each of these, and then on the next slide, I'll summarize some of the differences, and then through the next bunch of lectures, it'll hopefully become more concrete the difference between these two types of error. So modeling of turbulence, yes, this is a mathematical modeling error. So you're going to have lots of turbulence. We're going to have a lecture on turbulence modeling. What does that? How do people do turbulence modeling? So that's coming up with maths equations to describe turbulence is a field in itself. So that's definitely a mathematical modeling error. If you get that wrong, there's that could be wrong. Every variation in air density and conditions across the wing. So maybe if we repose this, align it with some other ones, might be to do with the inlet. So there would be certain weather conditions, certain atmospheric boundary layers that may affect the takeoff depending on your airport. So if you're setting up a model, are you going to take that into account or are you going to simplify that? So that's also a mathematical modeling error. So turbulence is due to type of the equations. This is to do with boundary conditions or inlet conditions to your model, how your model will interact with the rest of the world. Turbulence, wind and weather conditions, that's a boundary condition. Ignoring the surface of the wing. I'm not sure if I fully understand that, but maybe I can interpret it as a geometry mathematical modeling error. So maybe you don't capture the true surface roughness of the wind turbine. Does that make a difference? Well, it can. It can affect the skin friction or the so-called drag on the surface. So we can start to classify these mathematical modeling errors into different types. There's ones related to the boundary conditions, there's ones related to the geometry, and there's ones related to the material properties or material behaviors. Maybe turbulence, viscosity varies with temperature as well. These are the three kind of key areas. Also, you can add a fourth one, which is the governing equations. If you just make a wrong assumption about what the governing physics are, then if you leave out temperature and you don't solve the temperature equation, that's important. That's another one. So we'll come across over and over again that these are the four kind of categories. So the governing equations, how you simplify them, geometry, loading, conditions, and material properties. So numerical error due to mesh size number of nodes. Yeah, so we're going to talk about something called a mesh or the grid. We're going to split our geometry into all these small squares and triangles. And when we do that, we introduce what's a type of numerical error called discretization error. So we're going to learn about that, or it's sometimes called mesh error. So that's something that we can quantify, and that will be the focus of some of the labs, how to quantify this mesh error and to know that at least we can say that that mesh error is small, whatever about some of the other assumptions. Roughness, dirt, material property data, gaps and fixing. So this is the geometry as well. So mathematical modeling, it's assumption about the geometry. Incompressibility assumptions. So often in CFD, we assume incompressibility, but at higher Mach numbers, higher speeds, that might not be so good. So that would be an assumption or equation. So that's an equation assumption. Geometry, materials, loading, perfect manufacture, temperature change, atmospheric, weather, tip deflection. So if we just assume the wing is rigid, then we're ignoring the deformation of the actual solid wing itself. So that's like an error in our equations. So that would be what's called a fluid-solid interaction problem to solve for the solid and the fluid at the same time. So if that's important, the wing flex, that's also mathematical modeling error. So most of these are mathematical modeling error, tolerance of a numerical solution too large. So we're going to learn about iterative methods. So another type of numerical error we're going to learn about is called iteration error. And that's to do with if you're iteratively solving things, you have to stop at some point, and you don't stop when you get to zero, you stop in advance of that. So maybe that introduces a type of error. That's a numerical error. And let me just see some other answers came through as well. So time steps and meshing. So they're both related to this discretization error. If you solve a problem in time, it's done in a time marching fashion. You take a step forward 1 second or 2 seconds. So how big those steps are can affect the temporal accuracy as well. So that's a numerical error. So maybe the distinction is still not fully clear, but over the next couple of weeks, I'll give you more and more concrete examples on how to quantify different types of error, and hopefully that will start to make more sense. Okay, let me stop sharing this and go back to this. And where's my Zoom gone? Okay. Okay. All right, so here's a short summary of mathematical modeling errors. So for fluids, The governing equations, simplifications in the governing equations, here I'm just calling it simplifying fluid, and maybe certain assumptions around whether it's steady state or laminar or incompressibility or turbulent or not. That will introduce errors. And this one, boundary conditions, geometry should be here as well, and material properties. And numerical errors, we're going to talk about things like to do with the selection of the mesh or the time step, and iteration errors or rounding errors, and we'll learn what they are as well in subsequent lectures. So that's more just a reference. Okay, so I like this quote, and it's an important takeaway from just modeling in general. So if I'm presenting some of my modeling research to someone, sometimes they'll say, well, is this model correct? So if you ask that question, you're maybe missing the point of the model. So George Box I think he's alive, he's a British statistician. So he's a paper from the 80s or 70s, and he has this quote: all models are wrong, but some models are useful. So what does he mean by that? So normally I don't give a big load of text on a slide in a lecture, but in this case, I'm actually going to read this out because it's from the paper itself, and it's insightful. So now it would be very remarkable if any system existing in the real world could be exactly represented by any simple model. However, cunningly chosen parsimonious or like miserly models often do provide remarkable, useful approximations. For example, the law PV equals RT relating pressure, volume, and temperature of an ideal gas via constant R is not exactly true for any real gas, but it frequently provides a useful approximation. And furthermore, its structure is informative since it springs from a physical view of the behavior of gas molecules. For such a model, there's no need to ask the question, is the model true? If truth be the whole truth, then the answer is no. But the only question of interest is the model illuminating and useful. So this is a key point, that whatever model we're going to set up, it will never describe reality exactly. But that's not the purpose of the model. The purpose of the model is to answer some question and to provide some insight. So if I'm trying to design a better airplane, I might want to reduce the lift or drag. So the model doesn't have to describe all the physical mechanisms of air and how they break down at high Mach numbers or temperatures or chemical reactions or whatever. It just has to help me answer that question and provide insight into answer that question. Okay. Another comment, this guy's a French writer, lots of other things from 100 years ago. It's a complementary point, so perfection is achieved not when there's nothing more to add, but when there's nothing left to take away. So let me translate that into what that means for this module. So a better model isn't necessarily one which has more things in it. It's just one that's more illuminating. So often one that has less things, it's easier to interpret if it captures the key component. So if you're interested in a certain physical mechanisms, say lift and drag, you only need to include what's directly impacts the prediction of lift and drag. You don't have to model the, I don't know, like the fire engines on the runway driving by and their effect on the wake. That probably is an energy that you're trying to design. So more does not necessarily mean better. So that's in terms of the mathematical model, and then obviously we already said that once you have a mathematical model, and this is the kind of focus of this module, is how you solve mathematical models using numerical methods software. So specifically in this module, we were interested in types of maths problems known as boundary value problems, and these are described by partial differential equations. So I gave the spring example of a beam. If you have a steel rod and you apply force, there's a maths equation that will describe the deflection of that if it's not deflecting too much. That's a really simple equation. We do not need a finite element software to solve that problem. We can, but that would be silly. But we're particularly interested in what are known as boundary value problems. So boundary value problems are where you have a certain geometry, a certain domain. So that might be the region where air flows around an aircraft or a car. It might be a brake disc and a caliper, or it might be the actual material of the wing, whatever geometry we're interested in. And then we know something about the conditions on the boundary of that problem. So boundary value problem, the idea is we know the answer in some way on the boundary, and we want to find out what the answer is inside the boundary. So to put that a different way, if I draw this, I have to know how this interacts with the rest of the world. So I might say, well, there is a heat flux being applied here, there is a force being applied here, it's being displaced here in some way. So we know something about the boundary. They're called boundary conditions. So you have to have the boundary conditions everywhere. And then the question we're asking is, how can we calculate the solution inside? What's the temperature distribution throughout the domain? What's the displacement distribution? What's the stress distribution throughout the domain? Or the velocity and pressure in the fluid in this problem? So boundary value problems are the problems that we're specifically interested in. And there are a number of numerical methods that can approximately solve boundary value problems. So finite element and finite volume are the ones we're going to look at. So abacus uses finite element, ANSYS Fluent uses finite volume, so is up. But there's these other methods, finite difference spectrum methods. There's a family of kind of continuum of numerical methods that all have various relative methods. The reason we use these so-called approximate methods is normally there's no analytical solution for boundary value problems that are in any way complex. So if you have a infinite plate with a circular hole in it, then with a lot of complicated maths, you can get an analytical solution under very restrictive simplifying solutions. But if you change something like the hole's no longer circular, or we have a loss of plastic material, it's essentially impossible to derive an analytical solution. So that's why we use numerical. So throughout this course, we're going to adopt these kind of 7 steps every time we perform an analysis. And this is independent of the physics or the software. So whatever you're going to do after you graduate, or whatever you do in life after this course, if you go to use computational mechanics softwares, you may use Abacus, ANSYS, or Fluent, which we're going to use, but you may use other softwares. So it's not so useful, in my opinion, if I teach you very specific Abacus things if you don't use Abacus afterwards. So you'll notice that it's the same general procedure we'll use in Abacus, Fluent, and OpenFOAM. So that should mean it's easy for you to pick up a new software. So this is one reason I like to give 3 softwares as opposed to just focus on them. And so we're going to do a pre-analysis step. That's where we look at the problem and decide, well, how do we devise the mathematical model? And once we have that, we figure out how do we create the geometry and the mesh of that, and how do we set up materials loading at various numerical settings. And we solve it, look at the results, how do we interpret the results, and then we do verification and validation step to check are the answers right or wrong. It's very easy to get wrong answers. So as I said from the start, this is a kind of top-down approach to computational mechanics. So the course is aimed at as an informed user of these softwares, as opposed to, say, like CCM1 might be more aimed at the fundamentals of how you would actually write one of these softwares. So this is more about how you use softwares. In the pre-analysis step, there's 3 sub-steps. One is, what's the mathematical model can be solved, and what are the assumptions? And then 1B is what numerical approach are we going to solve the equations, and what errors might we expect, and then can we estimate those or limit them? And then 1C is, do we have some idea what the answer is meant to be like after we get it? So because these are complex softwares, you rarely will just run an analysis and assume it's correct. You'll have to verify in some way that it's correct. You might do use some simple hand calculation, check what other people did. Maybe there's some solutions in the literature or online that might be semi-relevant, and you can check, oh, is this the right order of magnitude? Because it's very easy to get wrong answers. And then the last step, just skipping to that, verification and validation. So in computational mechanics, these have very specific meanings. So in general speech, they're kind of synonyms, they mean the same thing. But in computational mechanics, they mean 2 very distinct things, and they're different. So verification in a short way means, did I solve the equations right or correctly? Whereas validation asks, did I solve the right equations? So if we think about that for a second, what does that mean? So validation, did I solve the right equations? So this comes back to the mathematical model. If temperature is important for calculating the lift and drag on a wing, and I ignore that, then it doesn't matter how well I solve that, how fine my mesh is, I'm not going to get the right answer. It doesn't matter if my numerical errors are tiny, my maths model is just wrong to begin with. I left out temperature. So that means I just solved the wrong equations. The equations didn't have all the physics that were important. So validation, a different way to put that, just means compared to experiments. But essentially that's all it means. Validating a model means a model has been compared to experiments, and you've shown that the model, mathematical model, and the ultimate numerical model describes physical reality to some degree of accuracy. That's what validation is. So when I ask what validation means, and you can check the final exam questions, you can probably expect a question on this. Did I solve the right equations? It's just, is it the right mathematical model at the beginning? So that's what validation is compared to experiments. Verification is a different thing. That just means that I set up the model correctly. So let's just assume the maths model is correct, that there's no temperature effect. So verification is things like, did I do a mesh study? Is my mesh fine enough? Or are numerical errors destroying the solution? So maybe you have the correct mathematical model, but you use too coarse a mesh, or you don't solve it with the right numerical settings. You have too large iteration error or discretization error, and you just get the wrong answer. So verification is doing those checks. And it can mean more general things. If someone is writing a software, they say it solves the Navier-Stokes equations, you have to check it actually does solve the Navier-Stokes equations. And so that's part of verification in this rate checks. So they're complementary. So a different way to put it, verification, you're going to get all these colorful pictures at the end of doing these analysis. So are they consistent with the mathematical model? So for example, if the boundaries are the correct quantities conserved, by the static analysis, I apply force on one side and force on the other side. Are they balanced? Check that if they're balanced. If they're not balanced, something's wrong how we set up the model. This is important at the start when you're learning to use the software, because the software might be correct, but you may have misinterpreted how to use a boundary condition or a material model. Or you thought that it wants the Young's modulus in units of gigapascals, but it's actually meant to be pascals. So verification is doing checks like that you're actually using the software correctly. And then one part we're going to focus on, numerical errors, are they acceptable? And then if we compare to some hand calculations, are they reasonable? And then validation is after you've verified the model, you're sure that numerical errors are small and related errors are small. Then you'll do a validation. So you'll compare to experiments. So sometimes you'll see in literature that people won't do a mesh study, they won't do any verification. They just set up a model, directly compare to experiment, and they say, it gives the same. This is a validated model. But it just could be by luck. Their mesh error was huge, but they made another assumption which canceled that out. So just by coincidence, they matched it. Or people will just change a few things in the inputs until they get it to match the experiment. And they're like, it's a validated model, this is great. So that's easier to do, but it is not a model that will generalize. It's not a model that will have great predictive power. And then there's a distinction here between calibration. So if you try change parameters in your model to fit an experiment, you're calibrating. That doesn't show that the model generally works. That's not a validation. So if you fit the material behavior, that's a calibration, not a validation. Let me jump out of this. Okay. Any comments, questions? Okay, for the next 15 minutes or so for the remainder of this lecture, I'm just going to go at a high level through setting up an example problem. I mean, at a high level, not specifically the software, and talk about some of the assumptions in the mathematical model. And at a high level, talk about how a finite element type method works. So in the next lecture on Monday, then I'm actually going to go through actual finite element method, and we can see what some of the details mean, and specifically some of these numerical errors, where they come from. So consider the following real-world problem, albeit it's a simplified. So imagine you have a plate, has a big hole, and it's bulged in some way, and before installing it, you just want to know will it yield or fracture at the surface level. So probably, like, one solution is you just try it and see if it breaks, or another solution is, based on experience, you have an idea of what the correct geometry will be, and then you just make everything way bulkier just to make sure it doesn't fail. And most of the time, that's actually fine. So maybe you wouldn't need to do an actual stress analysis for a problem like this. But there are applications where you really, maybe you want to minimize weight, or you really want to optimize this geometry, in which case you would do a stress analysis. So the first step in this pre-analysis is defining the mathematical model. And so this comes down to what governing equations should we solve? What are the key ones of interest? And how do we approximate the geometry? How do we approximate the material properties and material behavior? And how do we approximate the loading or boundary conditions? So that's how the model interacts with the rest of the world. Each one of these steps will add some assumptions, some errors. Once again, the aim is not to add no errors, that's not possible. It's just to make a model that's useful. One philosophy that's useful to model when, or to follow when setting up models like this is it's called the KISS philosophy. So it's an acronym for keep it simple, stupid. So anytime it's more of a programming thing. So anytime you have a decision to make around whether you should include something or not, or you can do something more complicated or less complicated, unless you have a strong reason to do the more complicated thing, just do the simple thing. If after doing all the simple things that the model is not sufficiently useful, then you go back and consider all of these simplified choices you made and try to determine which one is the more. So applied to the governing equations, you'll say, well, sometimes there's a 10-degree variation in the temperature in the lab. I don't know if that's important for affecting the yield stress. Should I include that or not? So KISS says don't include it, just do the analysis without it, check if it's useful or not, the model, then go back if you think that's a critical model measurement. So governing equations, I'm not going to dwell on some of the PDEs, but maybe I'll come back to that at another point. This is a Newton's law, steady state, basically. So there's divergence, this upside down triangle called lambda, divergence of stress equals 0. This just means sum over all surface forces equals 0. So it's just Newton's law for steady state, F equals 0, not NA, A is 0. So if you sum all the forces, surface forces, on any individual piece of material or the whole plate, they'll be equal to 0 if it's steady state. So this is the starting equation that's solved for typical stress analysis problems. And it has various different names. Sometimes it's called the principle of virtual work, and when it's in a different form, or it depends on which mathematical interpretation you're looking at. So if we start with this assumption, we're going to solve this for a displacement field. So the stress, when we assume a certain material behavior, will be given in terms of displacement. So we'll have a vector equation in terms of an unknown displacement field. So if I said, well, did we introduce any errors or assumptions? So, well, maybe we ignore gravity, we ignore inertia, like we assume acceleration 0, we ignore temperature effects. So all of these things may be important for your problem, but if you're not sure, you don't include them, and then you come back later and see if they have an effect or not. And the way you might do that is you set up a model without it. Then if it's not a useful model, you go back and include them and see that it affect the predictions that you're interested in. Then the geometry. So, okay, this is easy, you can draw this. But notice that I've also had to approximate the geometry. So maybe I didn't include these fillets. Are those fillets important? Maybe, maybe not. These circles maybe are not perfect circles. Is that important? There's certain surface roughness, that's important. Is that important? Do I have to include the bolts? I don't know, it depends how well I can describe the loading around. The key thing here is I'm just trying to say that you can always keep including more complexity, but that's not the goal here. The goal is to make a model that's useful. And then if it's not useful, when you create a simple model, then you go back and add more complexity. The wrong thing that people do, and many of you will do, simulation parts for your thesis project, is you might try and make this crazy complicated model, and then it doesn't work. You say it didn't work. And then someone comes to me and says, your model didn't work. I'm like, okay, show me what we're doing. And then it's this crazy 3D model where I don't know what's going on with millions of cells. Get a simple thing working. You can always add to a simple thing that works rather than start with a big complicated model that doesn't work, because that's just useless. So governing equations, geometry, material behavior. So of course, steel or aluminium or whatever this plate is, under certain loading conditions, you might get plastic deformation, permanent deformation. And under certain temperatures, you might get visco behavior. And depending if it's rolled, it might be anisotropic. It might be inhomogeneous, you'll have certain grain structures. That probably doesn't matter for this initial stress analysis. So I might assume the material is uniform and it's linear elastic. I'll assume the deformation is small. Linear elastic, and what material does it, law does it follow? Well, I assume Hooke's law, and then Hooke's law just means Young's modulus and Poisson's ratio. That's a good place to start. And then loading. So governing equations, geometry, materials, loading. That's the mathematical model. Once you have those 4 things, that's the mathematical model defined. So it's fixed here. Maybe I'll just say the displacement of these 2 holes is 0. But if you think about an actual bolt, the bolt will be pushing on one side and not the other side. So that's not exactly correct, but it's maybe an okay approximation to begin with. And then applying the loads here, well, if the loads are being applied from bolts attached to something else, they will apply a certain distribution of forces within those bolt holes. But maybe I can just apply a point load, but that might give a stress concentration. Is that a problem? Maybe I should just have a pressure distribution. So these are, just keep it simple first, see what you get. Does that solve your problem? Then you can make it, you can go back and include the bolts later. So that's our maths model. So we have to do that before we open software. And actually, for some mathematical models, possibly this one, there may be an analytical solution under certain conditions. So we made our maths model. Next, we have to make a numerical model. And this is where we use the software. So if we use the finite element method, it could be Abacus or one of various other softwares. And note though that when we use a numerical method, like Abacus, best case scenario, we get the answer to the mathematical model. We don't get the answer to real life. So if you just started with the wrong mathematical model, Abacus is not going to make magical predictions that coincide with reality. So best case scenario, your numerical model will give you the answer to the mathematical model. Whether that is useful in reality or not, that depends on how you define the mathematical model. So for example, if I said, we make our mesh smaller, does that mean your model is going to give predictions closer to reality? Maybe, maybe not. All we can say is when you make mesh smaller, numerical errors get smaller. That means your answer will get closer to the answer to the mathematical model. Whether that's close to reality or not depends on the assumptions you made in the model. So it's controlling these two different types of errors. That's the challenge for someone deciding things. Okay, so now I'm going to talk about numerical errors. They were all mathematical models. Numerical errors. First of all, the geometry. Remember, it's an idealized geometry, not real geometry. An idealized geometry. We're going to represent that by a bunch of triangles and squares or polyhedra or something like that. So this representation is normally called a mesh or the grid. And in finite element parlance, the intersection of the lines, they call them points or nodes, and then the shapes, they call them elements or finite elements. And so notice that just by splitting the space up into these squares or triangles, this is called spatial discretization. Discretization just means splitting into discrete parts. So this is a spatial discretization. This is actually an approximation of the geometry. So each of these little shapes has straight edges, the ones I'm using here. So this circle here is not an exact circle anymore. This is like a polygon, big polygon. So that means depending on the coarseness of your mesh, you can particularly see this for small holes. So see, these are no longer like really circular. That could be important depending on the application. Like if you really care about the stress concentration there, it doesn't matter how fancy your finite element method is, you will have geometry errors because the geometry is not very well captured. So that's the first type of numerical error, geometric approximation. Then we'll take our governing equations and in the next couple of weeks, we'll go through kind of physical derivations of the finite element method. I'm not going to go deep into some of the heavy mathematical approaches, but we'll take a physical perspective. But just for this lecture at a high level, essentially we take this Newton's law, sum of all the forces equals 0, and we apply that to each node. So we go to this node and we say, in terms of the surrounding elements, can I write this equation in terms of the displacement at this node and the closest nodes, the nodes sharing. So in some average sense, we're going to apply that here. So how do we do that? Well, we use this finite element theory. At the end, we start with this maths equation, a continuous equation, and then we write that in terms of an algebraic equation. What's an algebraic equation? It's just an equation like a simultaneous equation. It's like something multiplied by value here, something by value here, something by value here. So some number, which will depend on the geometry of the elements and the homogeneous thing, multiplied by the displacement at the red node, plus some number by this green node, plus some number by this green node. So we'll just get like one simultaneous, one of a set of simultaneous equations. So there's a bunch of theory how we get to that point. But that's essentially what the finite element method will do. We make an approximation around that. To do that, and we're going to learn about that, it will assume that displacements or stresses or strains are varying in some simple fashion, maybe linearly across these individual elements, or something like that. In reality, they might have some higher order polynomial variation, or maybe they're not easily described by our maths equation. So as we make these elements smaller, then the error here, this type of error gets smaller, this interpolation error, and this is called discretization error. So, or mesh error. So we're going to talk about how you can estimate that or control that. So we'll take this equation, and if you imagine here, we have 3 displacements in 3D for each of these nodes. So we've actually 21 unknowns here, scalar unknowns. We've 3 displacement components at each of the 7 nodes. So 21 unknowns. And we can do that same thing for every one of the nodes in our mesh. And then we'll just get, if we have 1,000 nodes in our mesh, we get 1,000 simultaneous equations. And then we can solve those simultaneous equations for the unknown nodal displacements. I've gone through that super quickly. The purpose here is just at a high level how the finite element method and similar methods work. We're actually going to go through the details of this. All those simultaneous equations, if you've taken a linear algebra course, you can write simultaneous equations in matrix form. A matrix multiplied by the unknown column vector of displacements is equal to a column vector, which is called a source. So this is called a stiffness matrix, is K. So you can write your simultaneous equations like that. You have, depending on how fine your mesh is, this K is a very large matrix. And then conceptually, how you solve that is if you multiply the left and right of this equation by K inverse. So K inverse by K will be I, that'll cancel out, and then you're left with K inverse by F on the right. So if you want to calculate the nodal displacements or nodal temperatures or nodal velocities or pressures, you just have to figure out what the inverse or calculate the inverse of the matrix and multiply it. Conceptually. In reality, how they actually do it may vary. Okay, I'm skipping over some of this text, and I know you haven't had an opportunity to read it, but that's more just for referring back. Okay, so this is me done, and so we'll have the lab tomorrow. Look out for announcements because I have to figure out what room we could use. And next week I'll start with some of the theory. Some of you will have problems installing Abacus. I can help you with that tomorrow. But hopefully we're ordering the computers today, so they'll be here in a set lead time of a week. So probably 2 weeks I'll have them set up as well. Very good, thank you. Cool, cheers. Bye.